conférence organisée par PhilEAs, l'association des étudiants en philosophie de l'UNIGE. Moi, je suis Romolo Borra. Je suis ici avec mes collègues Julia Merli et Robin Bianchi. On est les trois organisateurs pour cette année de ce cycle de conférences. Et ce soir, on a le plaisir d'accueillir un philosophe de maison, disons, un professeur de notre département ici à Genève, Christian Wüthrich. Bonsoir, monsieur. Du coup, professeur de philosophie des sciences et plus spécifiquement expert de la philosophie de la physique. Ce soir, il nous donnera un talk intitulé The Emergence of Spacetime in Quantum Gravity. Et pour aujourd'hui, également pour notre prochain rendez-vous, qui sera la semaine prochaine, Robin.
Oui, c'est ça, le 26 novembre aussi.
Okay, merci beaucoup. Nous aussi, nous sommes adaptés à la contingence historique, disons, à cette situation de la pandémie. Et on a transféré, du coup, notre cycle de conférences en ligne, ici sur Zoom. Mais pour le reste, il sera vraiment le même. Et comme d'habitude, le talk durera à peu près 1 heure. Après, on fera un petit 5 minutes de pause pour penser nos questions et on passera après aux questions. Et comme toujours, on donnera la parole plutôt et davantage aux étudiants pour pouvoir après passer à tous les autres intéressés.
Et...
les talks, pardon, Robin. Le talk de M. Wüthrich sera donné en anglais, mais quand même, pour les questions, vous pouvez les donner aussi en français. Et voilà, je pense que c'est tout.
Et juste pour ceux qui ne sont pas familiers avec Zoom, si jamais, alors bon, vous pouvez toujours décrocher votre micro pour vous manifester, mais dans l'onglet participants, normalement, ou alors c'est dans l'onglet chat, corrigez-moi, parce que moi, comme je suis host, je ne vois pas, il y a un bouton Raise your hand ou lever la main en français, si votre ordinateur est en français. Et du coup, comme ça, vous allez apparaître et ensuite, vous pouvez prendre la parole de cette façon-là. J'espère que c'est clair. Du coup, n'oubliez pas de laisser vos micros coupés pendant la conférence pour pas qu'il y ait des perturbations sonores. Et voilà. Et comme on a dit, bien sûr, les questions, elles peuvent être posées en anglais et en français.
Voilà, du coup, je pense que c'est tout. À vous la parole, monsieur Wüthrich. Et voilà, c'est tout.
Merci beaucoup. Thank you very much for inviting me to give this talk, and thank you very much for letting me have it in English, which is a little bit easier for me to fluently speak. I hope it's not a problem for you to understand. As was already said, there's no problem if you rather ask your question in French, and I may then respond in Fringlish or in some language. We'll see. Okay. So today I'm going to talk about the emergence of space-time in quantum gravity, and you might think, what the hell is this? I don't understand half of what this says. And it's going to be my goal today to explain this to you, what this is, what we mean by that, why this would be an interesting problem for a philosopher of science to look at. That's the goal for today. So I hope you all see the slides, which I'm now trying to, okay, there we go. So before I get going on quantum gravity, I would like to make a little remark about my methodology, what's going on in the background. And that has to do with my bigger sort of agenda and my bigger point of view of how I approach philosophical questions. And you could characterize this as an approach of naturalistic metaphysics. By naturalism, I mean something like the idea that philosophical theorizing has to be continuous with the scientific investigation of the world. So at least it must be consistent with our best science. That is a strict requirement, but that doesn't mean that it's always and necessarily philosophy which has to adapt to the science that somehow is in the driver's seat. It could also go the other way, but it's a requirement for naturalism that the two are at least consistent with one another and maybe a little bit more than that. So we should accept, at least sort of as a first step, that successful science is our best guide in understanding the world we inhabit. Again, that doesn't mean it's somehow a guide that could not possibly be overturned. Quite the contrary. I think there's, in the area in which I'm working, there's oftentimes problems with what physicists say and what they assert and how they interpret their own theories. And of course, that needs to be corrected. But what I mean to assert here in particular is that it's all else being equal, preferable to some sort of introspective analysis that philosophers often like, or some sort of trying to tease out intuitions we have about what space is like or what time is like, which are going to be important questions for us today. So rather than trying to intuit or articulate what we think is probably the case, it means we should look at the relevant science, if there is something in the science, and take this as a starting point. So a little bit more concretely, I will accept the following weak form of naturalism. This is a position you could call naturalistic metaphysics. It's the idea that no metaphysical thesis may be in manifest contradiction with facts established by our best science, in the sense that the physically possible worlds are a subset of the metaphysically possible ones. So the idea here, again, it has to be, it may not be in contradiction, which means it has to be consistent. It's not necessarily the metaphysics that needs to change. It might also be the physics, that's left open. But the idea here is that the range of possible ways the world could be according to science, to physics in particular, is going to be a subset of the ways the world could be according to metaphysics. So metaphysics gives us a more general range of ways the world could be, but the range the world could be according to our physics should be contained in it. So it better not be the case that there would be some ways in which the world could be, which are judged possible according to our best physical theories, but which metaphysics rules out as impossible. That would be a violation of naturalistic metaphysics. So in other words, metaphysics would be a priori deem impossible what physics would affirm is possible. So that's something we want to avoid. Okay. Now again, I realize this is a little bit more strongly formulated than I intended here on the slide. When I say metaphysics must accept as possible what fundamental physics considers possible, again, that's not supposed to be read in the sense that it's like physics, which first tells us what is possible, and then metaphysics has to follow suit. But that these two need to be coordinated. Even though I do think it's more likely that the metaphysics needs to be adjusted than the physics. But in fact, actually already when we formulate and interpret physical theories, there is always a lot of philosophical interpretation already in the background. So even though physicists would usually vigorously deny that, they are really in the business of metaphysics as well. They just may not know that, at least according to this point of view. Okay, now sometimes this will require that we give up some dearly held intuition or preconception we have about something, and in particular, as I'm interested today, in the nature of space and time. So we might have intuitively thought we have a good idea, a good concept or an intuition about what space and time are like, and that might be disappointed then. On this view here, if physics tells us that this is not consistent with the best, with our insights from physics, then we have to negotiate that, and it may be that our intuitions and conceptions we had prior to scientific theories, scientific theorizing may have to go. An example that's pretty famous or infamous, depending on your point of view about this, is Immanuel Kant, who argued, based on a priori considerations, that physical space has necessarily the geometry of Euclidean geometry. That means you have all learned in school Euclidean geometry, but maybe not under that name. Maybe you just called it geometry. But it's the geometry where if you have a triangle and you measure the internal angles and you sum them, you will get 180 degrees. It's basically if you think of two-dimensional geometry, it's the geometry of a flat surface and the figures you have in that, like triangles and circles and things like that, or polygons, etc. That's Euclidean geometry. And Kant thought that physical space necessarily has this kind of geometry. But unfortunately for him, physicists in the early 20th century, I should say, in the 19th century, it was considered an option, at least, that this might not be right. And in the 20th century, physics has come to conclude that, in fact, the geometry of what we would call physical space has been found to violate the rules of Euclidean geometry. In fact, you need non-Euclidean geometry to describe physical space. Now, you can think of that as, for instance, the surface of a sphere. That's curved, so you have curvature. On a surface of a sphere, the sum of the interior angles of a triangle is no longer 180 degrees in general. This can be violated. So you need a different geometry, you need different rules about what triangles are, and so on and so forth. And how you calculate the circumference of a circle and things like that. And it's now based on general relativity, which asserts that this is not the case. Physicists believe this was wrong. Okay, that's just one example in which of a way in which our intuitions might be disappointed. And general relativity, our best theory of gravity today, relies on a novel conception of space and time. Namely, I'm not going to characterize this fully, but just so you have an idea, space and time lose their independent existence. What we have instead is a four-dimensional unified entity, which could be called space-time. It has aspects, spatial aspects, and it has temporal aspects. But that's one radical innovation that we find in relativistic physics, actually already in special relativity, not only in general relativity. But the innovation that is added then in general relativity is that this space-time is curved, in the sense that in general the geometry will be like on curved surfaces and not like the flat geometry. And in fact, the structure of space or space-time can be warped and can be really funny, have funny shapes as well. Okay, so we need non-Euclidean geometry, the geometry of curved spaces. Here's just one picture that's supposed to illustrate that. If you have some sort of body coming near the sun on its path, it will be deflected like that, because space here is curved, as is sort of indicated here, near a massive object. This is supposed to represent the sun, so that's a very massive object, and something that swings by the sun like this, close by, will be diverted. Now, this is a huge exaggeration of the effect. The effect is actually much weaker, otherwise we would have it, found it much earlier. But this effect can be measured, and it's been confirmed so far. So the motto in general relativity is space-time tells matter how to move. By being curved, it tells that body here how it moves. And on the other hand, matter tells space-time how to curve, because space-time is curved where there are massive bodies like the sun or other massive objects like that. So that's, now we have a dynamical sort of picture of a four-dimensional unified thing that can wobble around and change and have all sorts of, can be in all sorts of ways that were considered completely impossible beforehand, even metaphysically impossible, necessarily false. And yet all of a sudden this becomes a way in which the best physics tells us the world is. So we find sometimes shocks to our intuitions, and in particular in space-time physics. And general relativity has certainly revolutionized our conceptions of space and time. Radical though it may be, I think it's fair to say that philosophers of science and naturalized metaphysicians have come to largely grasp what the implications of relativistic physics are for the nature of space and time. This is something that philosophers have thought about and studied the physics quite closely for a long time, and I think it's fair to say that it's broadly understood, at least in its main outline. However, this is not the topic for today. Today, really what I want to talk about is a much more radical shock that may potentially await us around the next corner. And it's a shock that's going to violate or challenge at least the following intuition that I'm sure seems fairly familiar. And this is expressed here by Larry Sklar. Namely, it's the inconceivability that reality, physical, material reality, whatever it is somehow non-spatiotemporal. So this is Sklar. He says, what could possibly constitute a more essential, a more ineliminable component of our conceptual framework than that ordering of phenomena which places them in space and time? Their spatiality and temporality, the spatiality and temporality of things is, we feel, the very condition for their existing at all. I mean, where here existing is like physical existence. Of course, there could be abstract objects, as philosophers know, like numbers or propositions. They presumably don't exist in space and time. Maybe there are mental objects which may or may not be exist in space and time. Maybe that's a separate question as well. Maybe if God exists, God might be an entity, an existing entity outside of space and time. So as it's formulated, it's a little bit too quick here, but this is what it's meant. It's like physical existence is closely tied to spatiality and temporality, to being in space and time. A world devoid of color, smell, or taste, we could perhaps imagine. It would be a strange world, a world very unfamiliar, a world very different from ours, but it seems conceivable. And similarly, a world stripped of what we take to be essential theoretical properties also seem to be conceivable. We could, for instance, imagine a world without electric charge, where maybe electrons would be neutral instead of negatively charged. Maybe matter is not constituted in the way of atoms. The atomic constitution might be replaced by some sort of continuum, perhaps, or some other strange thing. Perhaps there's a world without matter at all. That seems conceivable. It's kind of an empty world in some sense, but why not? But a world not in time, a world not spatial, except to some Platonists, or maybe more accurately, some Pythagoreans, I suppose such a world would seem devoid of real, that is, of physical being altogether. So it's like space and time are the preconditions of any physical existence whatsoever. It's certainly an idea that seems natural, an idea that philosophers have expressed at least since Aristotle, who sort of took it as almost definitional, that to exist materially as a physical object is to exist in space and time. So that seems a fairly straightforward assumption. But let's now move to quantum gravity. You might think, like, why? Why should we do that? Didn't we just say that general relativity was a perfectly good theory of gravity? Why would we need now a new theory of gravity, which I call quantum gravity? In particular, as you might have heard when if you read the newspapers, general relativity has recently been confirmed in spectacular ways. One spectacular way was the detection of gravitational waves about 5 years ago, for which physicists received the Nobel Prize maybe about 4 years ago or so, or 3 years, I forgot. It's gravitational waves is like a little, these are little juggles, little vibrations in the geometry of space and time that propagate through space and time. I told you it's a dynamical entity. And it's a phenomenon that already Einstein recognized is an upshot of general relativity. It's a prediction of general relativity, which it's a very small effect for the most part. So very difficult to detect, which is why it took so long for that to happen. But now we have it. It seems a spectacular confirmation. Similarly, the theory has predicted the existence of black holes. And as you may know, this fall, the Nobel Prize was given to 3 physicists, to one of them for a theory, for furthering or making important contributions to the theoretical understanding of black holes, and to 2 others for actually experimentally detect a black hole at the center of our galaxy. Again, this was a prediction, I mean, not the specific one, but the generic existence of black holes is a prediction of GR. So why would we need a new theory if it's been so successful recently? Well, because for one single reason, it presupposes that matter has no quantum properties. I'm not going to talk much about this today, but if physicists over the last 100 and something years have learned anything, then it's that matter, the matter of which we and stars and all animals and all material objects are constituted, have quantum properties. These quantum properties are weird and strange and unusual, and in many ways violate our intuitions about material objects as well. But that's established. If there's anything firmly established in physics, then it's that. And if given that general relativity cannot deal with that and presupposes falsely that matter has no quantum properties, it seems that we need to replace it with a theory of gravity that can do that. And this is what I'll call quantum gravity. Any theory which does that is a theory of quantum gravity. And we will need that in particular where these quantum effects become important. So in the early universe and black holes, for instance, physicists believe that in order to get an accurate description, an accurate theory of these things, we will need a quantum theory of gravity. Now the problem is, it's unfortunately so remote from our ordinary experiences, because I told you, you could test this in the very early universe and in black holes, but these are not like ordinary lab objects that any physics lab can produce. So we don't have any sort of empirical data that stands in need of obvious explanation or somehow violates standard physics. And it would be in need of some sort of theory of quantum gravity to explain it. I mean, there's some effects that we believe might ultimately derive from quantum gravitational effects, but that's not a very clear and clean constraint, empirical constraint. So as a result, what we have is we have many different approaches to trying to find such a theory. And among these are string theory, loop quantum gravity, causal set theory, many others. Now, this is one thing that many people have noticed and that we have tried to sort of systematically list in an article with Nick Coggett of 7 years ago. Nick Coggett is one of my most frequent collaborators and co-authors. You will come across his name several times tonight. So one thing, when you look at these different theories of quantum gravity, one thing you notice is that in one way or another, it seems that there's neither space nor time in those theories fundamentally. Or at least you could say there's either no space or no time. But I should say that the denial of space and time comes in degrees and differs from approach to approach. So this is sort of something that you realize when you do that. Now, what exactly is going on? I say here fundamentally. That means of the ontology, in the ontology of the theory itself, we do not assume that space and time are there. We assume the existence of some structures which look very differently from the way space and time look. That's what we find. So the idea, in order to speak in the language of physics, is that space-time theories, such as general relativity, for instance, sorry, I used the acronym here, that's general relativity, should be understood as effective theories and space-time itself as emergent. And you can think as an analogy, you can think of thermodynamics is an effective theory as well, because it doesn't describe the fundamental level. The fundamental level is described by some sort of quantum theory of the fundamental particles, plus some appropriate statistical way of dealing with many, many such particles, right? And temperature at that level doesn't exist. It doesn't make sense to say that this particle here has such and such a temperature and the other particle has another temperature. Rather, temperature, as I'm sure you've learned in high school physics, is the average, or can be understood in this picture as the average kinetic energy of a gas of many, many, many such particles. So temperature, the property of a certain region or room to be at a certain temperature, is something that emerges somehow from the fundamental physics. Or, you know, water. Water is constituted by molecules, which are constituted by elementary particles. None of these have the property of being liquid or, you know, other sort of watery properties. The watery properties that we associate with water only emerge if there's many, many, many of these molecules that somehow come together. And then we can even do hydrodynamics. Excuse me, we can describe how water in a river flows, what the dynamics are. But this presupposes, sort of ignores the fact that fundamentally water is something very different. So you're supposed to be thinking in the same way that we may have some fundamental constituents that make up the macroscopic world we know and love of tables and chairs and rooms with temperature and water that's liquid and all these things. From physics, that's very different. We have some sort of strange structures which are posited fundamentally to exist there, and from which somehow space-time emerges. This is supposed to be a sort of a block of space-time with the temporal direction going from bottom up. And these are two galaxies here, or my attempt to draw two galaxies anyway. And the galaxies, they move away from one another as time goes by, because of course the universe is expanding. That's what I've tried to picture here. But don't worry if you don't like the picture, that's fine. Just think of it that the space-time, the large-scale space-time structure, where it makes sense to say the distance between these two galaxies becomes larger over time, or something like that. This clearly makes sense to say at that level, but it seems to come out somehow from a reality that's very different. And to understand that and understand its implications, I've for several years been engaged in a larger research project, which we call Beyond Spacetime. So we try to sort of look at how the world looks like beyond spacetime. Once you give up the idea that there's fundamental spacetime, what can you say about the world, and what kind of philosophical problems arise from that? And that's together with Nick Huggett. Okay, let me give you some examples to sort of illustrate that. I originally planned it, I think it said so in the abstract, that I'm going to give you one example. And my idea was to give you like a little 20-minute or 30-minute introduction to one approach to quantum gravity to illustrate this. But I thought that maybe in a way that's too ambitious, and I instead I'm going to show you, give you a much more superficial view, but of several approaches to quantum gravity instead, so that you can see also a little bit the different ways in which maybe that disappearance of space and time manifests itself. So string theory. String theory is an approach to formulating a unified theory of all interactions. So this is in a way much more than just a quantum theory of gravity. It also tries to be a fundamental theory of how matter is constituted. It's supposed to be a theory of everything. Now, in the sense in which philosophers use that term, that's not a theory of everything, because it's not a theory of literally everything. It is a theory of everything in the sense that physicists use the term, which means a theory that can deal with all known fundamental interactions in the same theory. That is gravity, electromagnetic interactions, and the interactions, the weak and strong nuclear interactions that we find which are important for the constitution of matter. So that's the idea here. And in order to do that, what it does, it starts out from the standard model of particle physics, which is currently our best understanding of the constitution of matter, and it generalizes that theoretical framework to include gravity. That's the strategy it follows. However, in order to consistently do that, it turns out that the theory really is quite different from the sort of theories, the quantum theories of matter that we had before. It posits, for instance, something that looks like a 10-dimensional background space-time. And the things it contains in that space-time are closed vibrating strings instead of point particles. That's why it's called string theory. Now, is this 10-dimensional background thing here, which looks like it has 9 dimensions of space and 1 dimension of time, really space-time? Well, as my collaborator Nick Huggett has argued, and as is also explained further in this article co-authored by Baptiste Le Bihan, who's also another person in Geneva here who works in the philosophy department, that's a little bit too fast. And the reason has to do with the fact that we find in string theory many so-called dualities. And the duality is a relation between two theories, which establishes that the two theories are in some sense, in some physically relevant sense, equivalent. They capture the same physics, even though perhaps in their formulations they might be quite different. So that's a pretty deep and interesting, philosophically interesting idea. What are the conditions for two theories to be physically equivalent, expressing the same physical facts, even though prima facie they look very, very different? And it's much more different than just, two theories where you can find an easy translation between the two. For instance, if you have, general relativity formulated in French and general relativity formulated in German, these are two different theories in some sense, but not in a very deep sense, because you can find a pretty good translation manual that brings you back and forth between the two. But here, many of these interesting dualities relate theories which are not at all so easily related. And it turns out that string theory, it's in a way, it's a misnomer, not because there are no strings, but because there is no theory. What string theory is instead is a framework, a general framework in which there are several distinct theories. And some of these theories in that framework are related now by dualities. In other words, they are in some sense different formulations, but expressing the same physical facts. And at least some of these dualities seem to suggest that space is not real. There's one called T-duality, which says that the physics expressed using a closed string of a radius r is the same as the physics expressed by a closed string of radius 1 over r. So if you have very large distances, say, you get some description of the physics, but you can invert that, 1 over this very large number, and you get, in a way, to the very small, and that's exactly the same physics. Another duality, or maybe more appropriately called at this point a correspondence, is between its so-called ADS-CFT correspondence. It's an equivalence between the physics of a d-dimensional bulk and a d-1 dimensional boundary. So the idea is you can think of a sphere, of a filled sphere. You have three-dimensional interior of that sphere. That physics is the same, or it can be described in a way that is the same, that if you would project everything onto the surface of that ball and then describe using a theory that just describes what's going on the surface. So there's two theories which relate or relate to two physical descriptions of what's supposed to be the same, but the dimensionality is different. So this raises serious questions about whether distances and dimensions are real. But if the distances and dimensions are not real, are not fundamental, are not what's the same in both descriptions or in all descriptions of physical reality, then you may ask yourself, well, is space fundamental at all? Now, my collaborator Nick Huggett in this paper here has argued that we should not think of space as fundamental, but as something that emerges in string theory. Okay, the second example, causal set theory. Causal set theory is an approach which starts out from a core idea of general relativity, but tries to replace the four-dimensional space-time we find in general relativity with a discrete structure called a causal set. Here's a picture, which is a partial order by causal precedence relations. So you can think of these basic events here at the bottom as the initial events, and then this event causes this one and that one. This event here causes this event, and so on and so forth. As you go up, from the bottom up, that's the direction of how causality flows, how things are caused to be as it goes up. And it does so in a discrete way. So it comes in discrete chunks, as it were. So that's the main idea here of this theory. And strictly speaking, there is no time here. What we have is causal relations. That's the fundamental relation. So these relations that I drew here with a little line between these edges, these are causal relations, not temporal relations. But of course, I would grant that they look kind of similar to temporal relations, because we can think of like this event being temporally before this one and before that one, and this one before this one, etc., right? So maybe it's just terminological, so I'm not going to insist on that point. However, I want to show you that once again here, space seems to be absent. Now, if you look at the causal set here, I actually put on arrowheads here to indicate the direction in which the causation is supposed to flow, right? Because causality is an asymmetrical relation. Okay, so let's say, there's one event here now, this, snapshot with my finger. What is the space as of this time? What are the events which are co-present with my snapping the finger here? That's the question. Now, surely they're not going to be any of these events. Sorry, they're not any of the events up here, right? Because they're causally later. So they're not going to be co-present. They're not simultaneously in space at the different place in space. So they're not, these events here are not going to be any use to constitute space. And neither are these events down here because they're in the causal past of this red event. So eliminate those, which leaves us with all the green dots. Should we use all the green dots to say this is space as of this event here? But that would be unfortunate because now I have other pairs of events which are causally related, right? One which causally precedes another one. Okay, so that's no good either. So what we want is we want to insist that no 2 points in our set of space at that moment are causally related to one another. No one is causally earlier than any other. So this is one suggestion. That's not unique, of course. I could have picked this one. You see this one instead of these two, oops, down here. You see different choices satisfy that. But in the green-red set here, and in the green and red set here, there are no 2 points which are causally related. But now I have a problem because that resulting subset of the causal set is completely structureless. I said there's exactly one fundamental relation, namely a causal relation, and I told you space must be any set of events such that no 2 points are causally related. That means I just eliminated all relations from it. There's no structure. This is a completely structureless set. The only property it has is a cardinality. Maybe I can count the many points I have, in some sense the size, but I have no notion of dimension, so no topological structure as it's called in the jargon, no dimensionality, no geometrical structure like metrical structure like distances. I have nothing. So space has gone away in this picture. And of course, there is space at the emergent level, but not fundamentally. Now, let me get to the final example. That's loop quantum gravity. It's another quite well-known approach. And the idea here is that we start out from general relativity. And instead of going by that construction that's used in causal set theory, I use a recipe of turning a theory into a quantum theory that's been successfully applied elsewhere. So this cooking recipe is called quantization, and we try to apply it to general relativity. And if you do that, then it looks like the fundamental structure is going to look like these spin networks, as they're called. So this is again a discrete combinatorial structure where these edges are, you can think of as like little atomic parts of space, and the connections between them are adjacency connections. So that means this chunk of space is next to this one because they're connected, but it's not next to this one. Okay. Now the question is, you know, what about space and time in this theory? Well, space, I just explained to you, we have some sort of granular atomic structure of space, which is not the kind of space we thought we would find, or is not normally understood to be the structure of space. But maybe still it's kind of spatial, and we just found out that like matter is not continuous but atomic, maybe space is atomic as well. Well, that's true, there's some caveats, but the real tragedy in this approach is that we find that time has completely fallen out of the picture. You can actually look at the fundamental equations, which I haven't reproduced here, but there is no time in there. There's no little t that you would normally find, or anything in these equations which you could say, ah, this is time. This is how, you know, time enters the picture, or that it needs to be presupposed how. It's not part of the theory. And as a result of that, the world is kind of frozen. There's no meaningful way of speaking about change, things changing, things evolving, nothing of the kind. And some have said that this means that time is not there altogether. Maybe that's not quite right, but it's definitely forcing us into a view that's very, very different from what we know from, you know, or what we would intuitively think of a spatial temporal world. Okay, good. Now, sort of trying to abstract away, step back and look at the different approaches and what are the kind of lessons we can learn here. It's a work in progress. So all of this is like tentative. It's not final in any way. Maybe all of this is going to change. Maybe all of this will turn out to be false. Maybe the theories are correct, but the way I interpreted them, because I actually, you know, in the background, I did a lot of interpreting of the mathematics for you already here when I sort of tried to picture what the resulting view is, of course. Maybe I'm just wrong. Maybe I didn't understand the theory sufficiently well. That's certainly possible. But let's assume, at least for today, that this is not the case, that the fundamental theory of quantum gravity will in fact tell us that space and time are not part of that fundamental structure. I mean, that means the intuition that was expressed by Larry Sklar would just be false. Physical reality is fundamentally non-spatial, non-temporal. Could we make sense of that? Would this even be an option? Would this be somehow coherent? Could we have a physical theory or a theory of the physical world in which this is the case? And I remember, so 10 years or so, or even more, when Nick and I started to discuss this with other philosophers, some would just say, no, that's not even, you know, that's not even a possible way to think the world could be. You know, this just makes no sense. This is incoherent. And it was kind of difficult when we tried to argue with them why exactly it was they thought this was impossible. And here's our best reconstruction. So nobody ever said what I'm going to tell you now, except we did, I suppose. But maybe that's the worry, that there's a sort of a very particular form of incoherence in any theory that's not fundamentally spatial or temporal. And that would be the idea. The idea would be that it would be empirically incoherent in the sense that the truth of the theory undermines any empirical justification you may have for accepting the theory to be true. So it may well be the case that a theory is true, that the world, it correctly describes the theory. But if it is true, the kind of empirical evidence you have in favor of the theory, confirming that theory, could not possibly be the right kind of evidence. So the theory may be true, you may believe it to be true, but you could not coherently believe it to be true for the right reasons. because the kind of evidence that you're looking for, empirical evidence, would not be possible. And a theory denying the fundamental existence of space-time would then be apparently empirically incoherent, because the empirical justification of a theory derives only from our observing of effects of something that's localized in space and time. Maybe you say, this dial was here on Tuesday afternoon when I made the measurement, or this light bulb on Friday morning in the lab was green instead of red, or whatever. You know, data may take very different forms, or maybe it's you have some sort of sheet of paper with a printout of numbers, so of some quantity, right? So now I have a printout here that this is a spatial-temporal object, right? It's something that I have plots of print on a paper or something like that. Anyway, yet if such a theory were true, a non-spatial temporal theory, it seems that there could be no such localized something, that there could be no such evidence. So what's going on here? This is maybe to give you a little bit more of an idea, but very quickly, a reformulation of that same idea that's due to David Yates. You can think of the empirical incoherence as a tension between three propositions: that a fundamental theory is empirically coherent only if it entails evidence propositions, some propositions describing the kind of evidence we could have or the kind of predictions the theory makes. Evidence propositions attribute spatial-temporal properties to local beables. That means I measure this and that here and there, or if you measure or observe this, you will find this then and there to be the case, and so on and so forth. And the fundamental ontology of physics is non-spatial temporal. It seems as if at least one of these propositions ought to be rejected then. And this is what Nick and I do in this article. We save the empirical coherence of such a theory, but we argue that it must, of course, admit of an emergent space-time, because nothing in the tension assumed that the evidence is somehow at the fundamental level. The evidence is at the human level, right, of human scientists, how the world manifests itself to humans. That's at the level at which the world better be spatial and temporal. But that does not imply that fundamentally it has to be like that. It's just like when I say the water manifests itself to us liquid, or the fire manifests itself to us as hot, or things like this. That doesn't mean that hot and liquid are the way in which the fundamental existence have to be. But it means we have to understand how whatever exists fundamentally gives rise to things that manifest themselves to us in this way. So this fundamental structure, whatever they look like funny, weird strings in an indefinite, indeterminate space-time background, or spin networks or causal sets, or any of these things, they better give rise to a spatial and temporal world as we see it. And that's, if it does, then the problem is solved. Anyway, I'm seeing that we started a few minutes late, but I'm seeing that maybe I should rush a little bit. So that means any quantum theory of gravity has to go à la recherche de l'espace-temps perdu, in the sense that fundamentally space-time has gone, it's lost. Nevertheless, you have to find it. You have to somehow show again how it can emerge from these fundamental structures. That becomes an urgent and important task of any quantum theory of gravity. So the problem of lost space-time has so far not been completely resolved in any of the research programs I've mentioned, or in any other that I know about. And to solve this does require mathematical work, scientific work, technical work by the physicists, but it also requires philosophical work, because you have to get a grip on questions like, how can space and time be emergent at all? How can theories without fundamental space-time be empirically coherent? What are the criteria of success in the quest of recovering space and time? What exactly, in other words, is it that you have to recover or show to emerge from these fundamental structure so that the world is manifestly the way it is? Is it which aspects of space and time maybe you have to recover? I have argued, I'm not going to argue this, but I've argued that the criteria of success should be functionalist criteria of success. So taking a hint from functionalism, maybe if you've taken a class in the philosophy of mind, you may have talked about functionalism as a way to sort of offer a physicalist perspective or theory of mind. It's a similar idea here. So just like mind may somehow emerge from the brain in a functional way, or you can functionally reduce mental states to brain states, similarly, perhaps you can sort of spatio-temporal states or aspects of space-time functionally reduce to these structures of quantum gravity. Anyway, these are philosophical questions. But of course, you could also ask conversely, given or suppose that the world is like these quantum theories of gravity describes it to be, what would be the philosophical consequences and implications for that? So that's, in a way, the way you can think about this is, or the way I think about it is, you have physics and philosophy, and they're really, it's a two-way street. It goes back and forth. You can use tools from philosophical analysis to clarify and understand problems you encounter in the foundations of physics. But on the other hand, the insights you gain from fundamental physics will have to inform your philosophical views about all sorts of aspects about the nature and structure of our material world. Anyway, that's how I conceive it, and that's usually what I tell the Fonds National when I want money from them. Anyway, good. Now, why is this important? Because space and time, of course, are central in understanding the material world in both philosophy and physics. So this is a thesis I will defend by giving you examples. Space and time are presupposed in a number of philosophical and in most physical theories. They're assumed to be fundamental and are attributed, often implicitly, certain essential properties, like that they're infinitely extended, that they're continuous, all sorts of other things, perhaps, right? So this is my way of saying what the findings of quantum gravity will be are likely going to have implications for these theories of physics and philosophy. So we should pay attention. What's the argument? Well, I can just give you some examples. I hope that's enough to convince you. For instance, theories of identity, of material identity, how comes this thing, how comes this thing is my cell phone and not yours, right? And it's going to be, I can sort of tomorrow still identify this as that same object, or, persistence in general of objects, or persistence of persons, that is diachronic personal identity, over time, personal identity. In what sense am I still the same person as I was as the boy who played ice hockey, say, or, that's a question to which most theories which address these questions presuppose not just the existence of time, but time to have certain properties. Theories of causality are often based on spatial or temporal continuity and contiguity assumptions, not necessarily, but some of them certainly are. Theories of laws of nature interpret the laws often as dynamical prescriptions of temporal evolution of some sort of spatially extended system that evolves over time and changes. The concept of determinism certainly presupposes the existence of time. There's maybe a little bit more specific, the thesis of Humean supervenience by David Lewis, which says that the world is just a mosaic of particular facts obtaining at localized points in space-time. So that presupposes that there is a space-time in the first place, and so on and so forth. So there's many examples in philosophy like that, just personal identity, where one theory says it's that this personal identity is tied to spatial temporal continuity. So those of you who had introduction to metaphysics with me may even remember that, I hope, if you paid attention back then. This was one of the theories of personal identity that certainly presupposes the existence of space and time. Okay. Now in physics, this is not a course in physics, but in physics, it's even more all over the place. That doesn't surprise us, right? Because in a way, philosophy is more than about just the material world in a way. But physics really isn't. Physics is about the physical world, hence the name of that discipline. So you can see it's all over the place. If you look at Newton's second law, this represents space, this time. So there's a second derivative of a change in space with respect to time. Of course, notions of velocity and acceleration wouldn't make sense without space and time. This is a wave equation. Now, I don't expect you to understand the mathematics here, but the U's, again, are supposed to express spatial extent, and T, the T here, sorry, no, the U is some other magnitude. T is time, X, I are the 3 dimensions of space. In the fundamental equation of non-relativistic quantum mechanics, it's the so-called Schrödinger equation. Never mind what it is, but you see the T here? That's time. This is a derivative with respect to time. These are the equations for general relativity. Now, I definitely don't expect you to understand those. That takes at least a semester-long course to understand just this equation. But this object here is expressing the geometry of space-time. That's called the metrical field. This is full of space and time, and so is this object and this object. So even this object you can think of expressing or presupposing the existence of space and time. So of course, general relativity presupposes the existence of space-time. You can look at Maxwell's equations, Dirac equation, the Klein-Gordon equation, it's a long list of equations. Everywhere it's space and time assumed to be existing, usually infinitely extended, almost always as continua. Okay? So I don't know whether that's enough to convince you, but it is all over the place. So surely what we will find here is going to have implications for quite many things in physics and philosophy. So if space and time are no longer fundamental, but instead emerge from a non-spatial temporal discrete structure, then all these philosophical and physical theories will be, at best, approximately true theories of some sort of emergent phenomena, right? Then maybe, personal identity is not something that can be understood fundamentally, or any persistence through time of an object. Will have to be radically reconceptualized. Any of these physics equations, which seem so profound and important and fundamental to physicists when you show them to them, all of them seem to be presupposing the existence of space and time, and hence are really at best describing some sort of phenomena which takes place at the scale, at an emergent scale at which you have space and time. So let me conclude. So generically, space, time, or space or time seem to disappear from the fundamental ontology in quantum gravity, although the degree and the precise way in which this happens, of course, differs and needs to be carefully analyzed. Whatever these details may be, recovering the space-time, that is, giving a sort of an explanation in fundamental terms, an explanation that's scientifically and physically acceptable, becomes a very central task in relating the scientific image and the manifest one. In Wilfrid Sellers's memorable phrase, he said, look, the atoms I showed you, the fundamental particles, that's the scientific image of the world. The manifest image of the world is the world as it manifests itself to us. The tables and chairs and liquid water and hot fire and whatever we encounter and experience the world. In order to do science, we definitely need to connect these two. We need to explain how the manifest world arises from the scientifically described world, as it were. Now, that's a grand project. This will take more than just physicists. It presumably will take neuroscientists and cognitive scientists and maybe psychologists and who knows, many more scientists and philosophers of mind and philosophers of other areas to fully understand all of that. But nevertheless, to understand how space and time can emerge from something that's very different seems like the first step in such a project. So the relationship between physics and philosophy is, as I said before, a two-way street. On the one hand, quantum gravity induces a radical reconceptualization of central concepts of theoretical philosophy. On the other hand, quantum gravity is confronted by significant and ultimately philosophical challenges where philosophical tools can really help to get clearer and to progress. And by the way, incidentally, the causal set theory I explained really can be very directly traced back to a tradition in philosophy, not in physics, which starts with Leibniz and Kant and goes through the logical empiricists and much of philosophy of science in the 20th century, to then go back in the 1980s to physicists, actually, who take up this idea that maybe fundamentally the world is causal rather than temporal or spatial, and trying to understand it that way. So in a way, you could say physics and philosophy meet at the Planck scale. The Planck scale is the scale, tiny, tiny, tiny scale, where quantum gravitational effects are supposed to become important. So that's where you really need to have a quantum theory of gravity. And it was my intention today to show how deeply physics and philosophy are intertwined once you start to think about quantum gravity. The physics of quantum gravity has deep implications for philosophy, just as it cannot avoid the consideration of genuinely philosophical questions. Thank you very much for your attention.
Thank you very much for your talk. It was really, really interesting. I want to ask you, shall we proceed directly with the question, or do you want a break, sir, or anyone wants a break?
I am fine with just going on, but okay. I can also take a 5-minute break. That's no problem. It's really up to you, what you would prefer.
Okay. Does anyone want us to take a break? If it is the case, manifest yourself in the chat. Kirill, I see you're raising your hand.
I see one hand.
Okay. Okay, we shall take 2 or 3 minutes break.
Okay.
Then we come back to you with questions.
Sounds good. Yeah.
Okay, maybe we shall proceed with the question. I hope we will have the time to ask at least a few. I have some question, but if another student has questions, be my guest and ask it for me. No students has a question?
Oui.
Okay.
Bonsoir.
Yes.
Moi, je vais poser la question en français. Par contre, je suis pas très pratique de l'anglais.
Oui.
Ce que je me demande, en fait, ce que j'ai de la difficulté à interpréter, c'est donc dans toutes les théories de gravité quantique, on parle de structure fondamentale de causalité. Et ce que je comprends pas, c'est que dans notre manière d'interpréter la causalité, il se produit un changement partant d'un point A à un point B qui implique un mouvement. Il y a un changement, il y a un mouvement, et donc il y a aussi une vitesse. Et donc, ça voudrait dire que ce serait une structure causale qui n'a pas de vitesse, et donc elle se produirait de façon instantanée.
Okay, so are you thinking of this structure, for instance, the sub? Or, yeah. Okay. Now, this is the idea is really supposed to be that you don't think of causation as sort of change and therefore being some sort of movement in time or something like that. It's not like, you know, this causes that thing to move by pushing it because this moves in space over time like this to move to the other thing or something like that. That's exactly not how you should think about this. This is explicitly, you just have, in a somewhat abstract sense here, a relation of causal precedence. I say precedence because I want to express somehow the asymmetry of the relation. But it's really only derivatively or secondarily a temporal relation. It is causal relation. This is cause, effect, etc. That's how you should think about this. Now, you may ask the question, but how is this different from a temporal relationship? Why is this not just earlier, later, earlier, later, earlier, later, or something like that? And that seems fair enough. It is really very similar, like a temporal precedence relation here. So this is why I didn't push the view here that time is eliminated. Maybe time is not eliminated. Time is just really encoded somehow in these causal relations. That's what it really is. But the point in this example was more that space is not there in any straightforward sense, at least not fundamentally. So of course we have, again, like these little chunks, these little events, which in some sense are those things which constitute space-time in the sense of giving rise to space-time. So they must be the sort of fundamental things that give rise to and sort of combine in ways to make space and the notion of distance meaningful, that we could say it's, you know, from here to here is 30 centimeters or something like this is meaningful, right? That's important, but it's not something that you can read out of the structure here, because as I've argued, a meaningful notion of or translation of the idea of space at the time would be something like the green and red dots combined here. But by definition, there are no fundamental relations that obtain between them. Therefore, there's no spatial structure. Spatial structure arises somehow out of the totality of all these things in their structure once you have that. That's the way it's supposed to be, secondary, non-fundamental. I don't know. I hope this was helpful. But it is puzzling, I agree. I mean, it's not so easy at all.
Okay, someone raised their hand, so you can ask your question.
Was that me, Robin?
Yeah, of course it was you.
Okay, thanks. Hi, Chris.
Hi, Sakshi.
I was curious, what are the implications for the abstract nominal debate about entities? Because we think about, abstract concrete debate about entities. Because we define concrete entities as those that live in space and time and that have causal relations. So do we just redefine what it means to be concrete, that these entities live in this more fundamental structure, or does it do more violence to our intuitions about what concrete is?
Good, great. That's a great question. It's something that's, I could have talked about this, or maybe I should have talked about this. This is another thing that philosophers complain to us, that this just doesn't make sense because it would sort of eliminate the idea that there's a distinction between concrete entities, which are those entities which are in space and time, and abstract entities, because, you know, a causal set like that would not be in space and time and therefore would be an abstract object. But, you know, that just seems strange, given that, so we're just, you know, or in other words, does physics become mathematics? You know, there's no sort of distinction between the two. And to this, I think that, yes, it's true, you may have to give up your criteria to distinguish concrete and abstract objects, because neither space-time nor causality are going to work in general, depending on which approach we choose and so on and so forth, but it's not going to work. But that doesn't mean there is no such distinction. The distinction, again, has to be made, however, through the emergent level. So physical, or in some sense, physical or concrete structures are those which are of the kind that can give rise to space and time, that can give rise to the world as it manifests itself to us. Abstract objects like sets or propositions, things like this, cannot give rise, however they combine, they cannot give rise to rise in space and time. But these structures, they have to, as I argued, to also solve the problem of empirical incoherence. If we've solved that problem, therefore, we do have still, I think, a criterion to distinguish the two.
Thank you. So if I understood, it means redefining what concrete means, but maintaining that distinction.
So in a way, you maintain it. You want to say that, yes, so the concrete things or entities or structures are those things which have in some sense to do with space-time. That's not false. It's just the way you defined it originally was wrong-headed, because you presupposed that there is space and time, and given that, we can then sort of check for each object whether it lives in it or not. And that's not how the criterion has to be applied. You first have to see which are the kind of things which actually give rise to the space and time, and only then will you come to understand the distinction.
Right. Okay. Thanks, Chris.
Sure.
I have some question, if I may. During your talk, when you talk about emergence, I wondered if emergence is meant here to be understood as some kind of supervenience between fundamental properties and space-time, because in fact I was thinking of David Chalmers' book The Conscious Mind, and when he talks about supervenience, he proposed a kind of thought experiment in which he considers that let be a kind of omniscient God that will only see the fundamental property, the physical property. This God could deduce the biological property from the physical properties, but also if this God does not possess the concept of the biological properties, he could not see, in a sense, the biological properties. And I wondered if this, in fact, applies to the case of emergence of space-time, and also if, in the end, we should almost consider space-time as a biological properties that organic being project or consider the world as having.
Okay, good, great. Yes, that's an excellent question and something that's certainly discussed among philosophers. Now, I should say, before I say anything more than that, that there is debate going on about this question. How should we understand the emergence that's sort of at work here? And the reason why this is not a trivial question is because physicists are actually the ones who started to use the terminology. They started to speak of emergence of space-time. Because to them, it seemed like, okay, it's kind of, not fundamentally there, the distance, for instance, given the T-duality that what has a certain distance and what has the inverse distance is physically the same. That means distance as we know it is not fundamental, it sort of is emergent. That's the language physicists introduced without really reading Chalmers or any philosophers who have thought about emergence and supervenience and what exactly it means. So I'm not going to cover all the debate. I'm just going to tell you what I think is the case. Maybe that's or at least a starting point. So I think the way we should think of emergence here is that something it's certainly not in the way that philosophers, in particular in the philosophy of mind, sometimes use it in a sense of strong emergence. That it's that there's a non-reductive relationship, that somehow the strongly emergent entities cannot in any way be understood in terms of the fundamental existence or something like that. That's not a useful way to think about it. I think it's really more like temperature and liquidity and things like that, sort of, macroscopic features of the world in some sense, which can nevertheless be reduced and understood in terms of the fundamental things that exist. Like, the atoms and the way in which they combine to form molecules and liquids and gases and things like that. So I think the emergence here has to be understood at most in this sort of weak sense, in which you can have a reductive relationship that still obtains. And then some philosophers have complained and said, but that just means, the physicists don't know what they're talking about. They're abusing the language here. We have introduced and defined emergence in this sense that that's okay. If you insist on that, then sure, then emergence is the wrong word. I just don't think it's a very interesting complaint because it seems like merely verbal. But the interesting question is the question you posed. What exactly do we mean by that? And we mean, I would think, a broadly reductive relationship that is probably going to be stronger than supervenience. I mean, we would supervenience to obtain. We would think that, right? Because there couldn't be a difference at the level of space-time without there being some sort of difference in the fundamental structures. But inversely, there's going to be many differences in the fundamental structure that's not going to make any difference at the larger scale. They're just, at the scale we are, they're not going to be noticeable. If there would be an additional little collection here or there, say, or not, we will, our macroscopic perception of the world will be completely unchanged by that. So in that sense, yes, supervenience will certainly obtain, but we will want to say a bit more about it. We would actually be able to offer a reductive account, give a reductive explanation of how that works. That has to be the goal. So in a way, it's much more ambitious than just to identify what relation it is. But I think as a first step, it's helpful to think sort of what do we expect? And this has to do with the success criteria I mentioned somewhere. I'm not sure now. Oh, here. No. Oh, here. So what are the criteria of success of recovering space and time? That's certainly, first of all, a necessary condition is to understand that relationship. But secondly, then to actually be able to follow through with the reduction, I think.
Okay, thank you for your answer. Does anyone have a last question? Romulo?
I have a last question. If anyone has no question. Okay. But how can we speak about the fundamental properties of physics? Because in a certain way, your accounts assess that these fundamental properties are inscrutable. Like we don't have any epistemic access to these properties or their nature, but they are, like, for instance, deduced by the more common scientific properties like space and time. But so how we can firstly discover these properties and speak about these properties, and also after that, how can we speak about the relation between these fundamental properties and these relational properties in the sense of how it plays these relations?
Good, yeah, great. That's another very good question. Now, in practice, it works something like this. Physicists, as I said, have no measurements or no sort of empirical access to that. In that sense, it's inscrutable, even though inscrutable may be a little bit, so in the sense of Chalmers, maybe a little bit more stronger than what these are. But they're certainly very remote from our empirical access, and they may also be remote sort of cognitively, in the sense that they're very different from the kind of properties that humans find conceivable and imaginable and so on and so forth. In practice, the way it works is physicists use principles, ideas, mathematical techniques that have been successful elsewhere and try to extend them, to generalize them, to push them further, to combine them in new ways, different way, new combination of principles, and then find a consistent mathematical expression of the resulting theory. That's already a highly non-trivial task, because the mathematics that is required for many of these approaches is really very advanced and demanding. So this is something that you have to study for many semesters as a graduate student to really start to understand the mathematics. But it can be done. You could start to sort of offer interpretations of the mathematical formal theory, trying to, in other words, articulate in humanly understandable words what you take to be the physical significance of these mathematical formulae, of these mathematical objects. So in that second step, you no longer do mathematics. You really, you understand mathematics as a language in which you express these fundamental truths about physics. And it's very difficult, highly non-trivial work to tease that out, to somehow relate that to how we can conceivably think about the fundamental nature of the material physical world. And that's, in my view, that work is just at the beginning, to be honest. This is very difficult, very, it takes many really smart people and many years of hard work to try and start to get an idea of this. Is there a guarantee that we will succeed? No, there isn't. It could be that we are somehow forever meandering around trying to use the kind of concepts we can use, trying to understand the fundamental structure of reality in ways that make sense to us, ways in which are somehow scrutable to us, and that may not work. The world may simply not be kind enough to be like that, to be humanly understandable. There is no guarantee. But what other options do we have? I mean, we have to give it a try, right? And try to do as well as we can. But you're right. I mean, there is a clear danger that maybe at the end of this, we will not get to the bottom of it. Maybe one last thing. The hope, of course, is that eventually we will be able to have a sufficiently developed apparatus of the theory that allows us to derive concrete predictions for observations and measurements. That would be the ideal, and that then, of course, is an extremely important criterion of success in physical science. If we can somehow predict something, some novel phenomenon, something that is measurable, observable in maybe some complicated, very highly difficult way that requires 1,000 engineers to work on this for 100 years, maybe so be it. But maybe there's something about black holes somehow that we can observe that none of our currently existing theories has predicted, but that some of these new theories predict, and then one day we will find it. That will be taken as a strong sign that maybe this theory is on the right track. Right.
But so if I have good understood, it would be the methodology of this project. It will be really a priori, and it's like working on some theorems.
Sorry?
It's like working on starting from some basis and to derive the implication of these fundamental elements, and after that, but only after that, to check in a posteriori way if our predictions are correct.
In some sense, yes. I mean, it's not fully a priori because the basic principles and techniques from which you use are principles and techniques that have been extremely well confirmed empirically, a posteriori, in earlier physics. So it's not completely detached from that. So what you do is you kind of try to use and mix and match things that have been successful in the past, empirically successful, and to somehow try to use those elements to create something new. You're right, in a way that's for now sort of disconnected from empirical confirmation. It's a priori. It's mostly mathematical. In actual practice, it's very mathematical when you do that. It's not a conscious choice that this is a priori in this sense. It's more like, well, we just don't have any a posteriori, data. We don't have any observations. We would, if we did, we wouldn't wait until 100 years from now. We would already apply now, but we just don't have any. So it's born out of a necessity that for now, yes, this is mostly a priori work. And as you can imagine, that's the point where then people start to think about, can we confirm a theory maybe in using non-empirical methods? Which, of the three theories, I told you about string theory, loop quantum gravity, causal set theory. How do you assess these theories? Can we evaluate these theories before we have any observations? Can we maybe say that's the best one? Can we toss them out? I mean, what criteria do we use? This also becomes an important question in philosophy of science, of course. All right.
Okay. Thank you for your answers. I guess we'll stop here.
Thank you again for having me. It was a pleasure. And don't, you know,
It was a
I
pleasure
hope
to have
we
you
can see one another again in the spring semester in person. And if you're interested to have more questions, don't hesitate to contact me. Okay?
Okay, it is very kind of you. Thank you.
Thank you very much.
It was a great pleasure to have you.
Thank you.
Totally.
Thank you.
Thank you.